Hello everybody and welcome to my living room amongst all the jigsaws and bits like that. Now, don't be put off by the word physics, because you might be one of these people who thought, I never liked physics, or I always hated physics, or I never did physics. Well, this little talk's just for you in that case, because there's no maths and no equations. If, however, you've got A-level physics, then look, you know all about this, so why don't you go and do something useful like mow the lawn or paint that window frame that you're supposed to be doing. Anyway, let's carry on, because today's talk is all about turn that radio off because I'm trying to do a lecture. Thank you. Okay, all about sound. And I even have my own subtitles, you see. And in fact, if any of you are hard of hearing, I said if any of you are hard of hearing, I've got louder subtitles, all about sound. Now, sound is a series of vibrations. That's about it, really. Not much more to say about it, but I can elaborate a bit if you'd like. Would you? Okay, good. Let's go on a bit more then. Now, if you get something to vibrate, it makes what we would call a musical note. Now, take this bowl from Nepal. Well, no, don't take it, but because I want it. But it's a singing bowl, made of metal and a piece of wood. And if we stroke it nicely, it vibrates and lets out a particular note, or, as we physicists like to say, frequency, but more about that later. We can do the same, as you probably know, with a wine glass, but it doesn't work first time. To make it a bit wet. Now, everything vibrates at its own particular frequency, or note, depending on what it's made of, or how big it is, and how thick it is, and so on. And I'm doing this all the time, because it's really annoying, isn't it? That's why I like to do it. Now, what I'm going to do is put some water in the wine glass, and I want you to listen to the different notes. First of all, on its own. Now with some water. It's a lower note, a lower pitched note, or a lower frequency, and that's because as it's a bit heavier, it can't vibrate quite so quickly. So it vibrates slower and gives out a lower note. Okay, so that's all about vibration from particular things. And really, all I'm doing, when I'm doing either my finger on the wine glass or this, I'm just, with friction, it keeps catching it and letting it go, catching it, letting it go, catching it, letting it go, which is exactly the same as if you're playing a violin. The bow keeps catching the string and letting it go, catching it, letting it go, and it makes it keep vibrating. And so therefore, we've got vibrations which are giving musical notes. Now this is a little video showing a loudspeaker playing in slow motion. A loudspeaker is basically a cone which is made to vibrate backwards and forwards. There's a bit of rubber around the edge so it can move. And it vibrates backwards and forwards at the frequency which you want it to, or as fast as you want it to. But this is slow motion one. So what it does is it pushes and pulls the air immediately next to it, which passes on the energy to the next one. Now we can see how that works in this nice little demonstration here, which represents big blue molecules. They don't really look like that. And as we give energy to the left-hand ones, they pass them on to the next ones, and the next ones, and the next ones, and so on. But notice that they just vibrate backwards and forwards in the direction of the wave. And here's a further one which shows it perhaps a little bit better, imagining that the loudspeaker is the red thing on the left, and we can see the waves of energy definitely passing on. They're going to go up to your ear, and the molecules themselves are just vibrating backwards and forwards.
This is called a longitudinal
Okay,
wave.
so let's have a look at the physics of musical notes. Now we all know that musical notes look like that, don't they? Or maybe they look like that. And if they look like that, they might even look like that. But do we know what they sound like? Well, I told you that musical notes is a series of vibrations. And if we make something vibrate at 256 times a second, that's what we call the note of middle C. I'll just play it on the piano, which you can't see at the moment. It's over here. And the piano's a bit flat, so it's not quite middle C, but me, 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 me. 256 vibrations a second. Now, we physicists call vibrations per second hertz. So we'd say that the frequency of middle C is 256 hertz. And hertz is spelt the same as that very famous Dutchman. Remember him? Hertz van Rentel? H-E-R-T-Z. Okay. So, a series of vibrations, or a series of pulses if you like, which come from the thing making the noise to your ear. Now, what I've got here on the phone is it's called a signal or frequency generator, and it can make little pulses, which hopefully you'll be able to hear. And if you can see it, it says 3 per second. Now, is that a musical note? I don't think you'd call it a musical note, but let's increase the frequency. 8 a second. Okay, now let's do it more. Sounds a bit like a motorbike, doesn't it? But definitely a note. Not a very nice one, but it is a note. And the higher the frequency, the more the vibrations a second, the higher the pitch of the note. That's very high, 2,690. There. So the higher the frequency, the higher the number of vibrations a second, the higher the pitch of the note. Now, if we want to go and talk about music, if we double the frequency, in a musician would call that going up 1 octave. I'm just trying to get out of this now. Here we are. So let's just try that. We'll have, let's just a random one. This says 107. Let's go to 214-ish. Remember that note? There. Same note, but 1 octave up. Double the frequency. Okay, we can remember that. We'll come back to that later as well. Now, the human ear is a marvellous instrument because, as you know, that's how we hear sounds. And when a musical instrument makes its vibrations, that longitudinal wave comes towards me, the molecules near me start vibrating, and then the molecules right next to my eardrum vibrate, which send all the information through to the inner ear, and there's lots of bits in the cochlea, that's the curly bit like a snail, which vibrate for different frequencies. And the human ear can hear from 20 vibrations a second, 20 hertz, all the way up to 20,000. So it's a huge range. Now, you and I are a bit more senior than some, and so in fact we can probably only hear up to about 12 or 14,000. You lose the higher frequencies ability when you get a little bit more senior. I used to have great fun at school with the signal generator. I'd put it on very high and say, right, we can't hear that yet, so I'm going to turn it down. Put your hand up when you first hear it. And I'd go like this. And when we got down to about, I said, 25,000, 20,000, and the first hand would go up, then another, then another, then another. Then I'd say, oops, sorry, I've forgotten to turn it on. But basically, they could hear up to about 20,000. I could only hear up to about 13,000. And they just laughed when I put a loudspeaker right next to my ear that they could all hear, and I couldn't hear it. You're just deaf to higher frequencies. Well, howdy y'all, here's me and my old guitar, and I'm just going to show you something about musical notes on here. Well, we all know that this can make musical notes by making the string vibrate. Just choose one string. Okay? And the frequency of that depends on various things. But if I was to make it vibrate with only half the length by putting my finger halfway down, then it's a shorter string and it vibrates at a higher frequency. If I halve the length of the string, and we physicists would say we're halving the wavelength, then I double the frequency. And so therefore it should sound 1 octave higher. Let's try it. I've got a marker on here so I get it right. Here's the ordinary one. Now let's push that one. It's the same note, 1 octave up. Half the wavelength, double the frequency, up 1 octave.
Now when we plucked the guitar string nice and gently, it vibrated in its simplest possible mode. They called this the fundamental frequency, and it looked like this. It was held at both ends so it couldn't move at each end, and it could vibrate to a maximum amount in the middle, fundamental frequency. But if I did it a bit harder, then I could make it vibrate like this. And so a string can vibrate in not just the simplest mode, but other modes as well, and there's more after this. And these are called harmonics. That's the second harmonic, and then if we had 3 loops, it'd be the third harmonic. And notice each time you get a higher harmonic, the loop is shorter, and we say the wavelength is shorter. Now, the actual note emitted from a string isn't just dependent on making it vibrate in different ways, but it's dependent on 3 other things. It's dependent on the length of the string, as can quite clearly be seen here. And by the way, the big bit on the bottom of the harp is the sound box, like on the back of a guitar, to make the air vibrate and make it sound louder. The note can actually also depend on the tension in the string, as you probably know if you've ever tried to tension a violin or a stringed instrument. And it can also depend on the thickness of the string, which is shown here with an electric guitar, with very thin ones for the higher notes, higher frequencies, and a thick one for the lower frequencies.
Now, here's quite an interesting thing to do with vibrations and using the frequency generator. And I'm going to use 2 frequency generators this time. This one, if you can see, is set on 600 Hertz. Now I've chosen that frequency because A, it's very annoying, and B, my favourite airliner was a VC-10, and when it started its engines up, they used to go at about that frequency, and that's the noise it made. What I'm going to do is bring a second one in. So this is an engine number 2 starting up, and I'm going to put this here. And this is on a different frequency, 570. I'm going to play the 2 together, so you just listen and see what we hear, or hear what we hear. Can you hear good? What I'm going to do is slowly make this one closer to 600. Can you hear it pulsating? It's just like engine number 2 starting up on a VC-10. The effect is called interference. It's 2 sound waves adding together and taking away from each other when they get in step or out of step. And what we hear are called beats. The frequency of the beats is the difference between the 2 frequencies. That's on 600, this is 595, so there should be 5 beats a second, 4 beats a second, 3 beats a second, 2 beats a second, there should be no beats at all now because they're both perfectly in tune. Let's turn it off. I believe that's one way that you used to be able to tune pianos, by listening for the beats. And when the beats were as non-existent as you could make them, then basically it was in tune, one note with another. Okay, onward with our frequencies. We've done waves in strings. Now let's get air vibrating this time rather than just the strings. And we have air columns. Now you've probably all blown over a pen top and made it make a noise. Okay, that's how we get the air to vibrate. And what's happening is it's able to vibrate a lot at this end. It goes like that. But at this end it can't vibrate because there's a wall blocking it in the way. So you've got no vibration and lots of vibration. And so therefore inside we get a wave set up that makes all the other molecules vibrate and go off to your ear. And if we want to make the air column longer, something like this is a very cheap and nasty one, but it does sort of work. So let's just have a longer air column. Again, by blowing in here, I'm making the air inside vibrate. Lots at this end, not at this end. And so that makes the musical note of a particular frequency. For more,
let's look at the mechanics then of the flute, or let's think of a recorder, because you've all played a recorder at some time or other. Now this representation shows you, at least think of the top one, the tube of the recorder, and at one end it's fixed, just like we said with the pen top, and the other end is open so it can vibrate a lot. The right hand end, it can vibrate a lot. So think of that as our recorder tube. And here we are with a picture of it shown, and most people think that when you blow in one end the air comes straight the way through and out the other end, but not so. What actually happens is inside there's a block, so that when you blow in the air comes out but goes past a tiny gap, and the air going past that tiny gap makes the air inside the air column vibrate and give us our note. So here you are with all your fingers on the little holes, and basically the length of the flute is the length of what we saw before. It can vibrate at the right hand end but not the left hand end, so the particular note comes out. Now when you take one finger off, so there's a hole instead of a finger at the bottom end, it means that the air can vibrate there, so effectively you've got a shorter tube. And so on, you've got an even shorter tube, so the more fingers you take off, the shorter the tube that's vibrating, the higher the frequency, that is to say, the higher the pitch of the note.
Now, some instruments are brass instruments, like trumpets and trombones and things like that. And to make the air inside those vibrate, you have a mouthpiece, and you've basically got to blow a raspberry in it. You've got to go like that, just like that. Now, if you do that into the mouthpiece of a trumpet or trombone, it makes the air inside vibrate and makes a particular note. That's how we do it. Believe it or not, that's physics. That's really good physics. It's called the Bernoulli effect. When air flows past a surface, the pressure lowers. I could show you that with a bit of paper. It's a principle of flight. Watch. Air pressure, same on both sides. Blow over the top. The pressure lowers, it goes up. Clever, eh? So what happens is when you build up the pressure inside and blow air out, and the pressure is enough, it opens the lips, the air goes out, but that lowers the pressure, which pulls the lips closed again. And so hence you get a vibrate. Just like that. The same is true with other exhalations of various sorts of winds as well. That's why makes a noise. So you do that in a brass instrument. Now let's see how brass instruments actually work, starting with the bugle.
Now a bugle is a very straightforward instrument, and it's basically a long tube which is bent round and round to make it shorter and easier to hold. It has no keys on it at all. It just simply is a tube, and that means that you can make the fundamental frequency, or you can do harmonics. And with a bugle you can generally get 4 or 5 different harmonics, and if you think of bugle tunes, they've only got 4 or 5 notes in them. For example, do 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 do. Okay, good singing, but only a few notes. So the bugle is limited in that. You get the harmonics by blowing harder in different ones. So let's lead on from the bugle onto the trumpet. Now, most people think that the trumpet has only got 3 notes because it's only got 3 things sticking out the top, but not so. Once again, the trumpet is a very long tube which is bent round and round, and it has these 3 buttons, but they are not notes, they are actually keys which open valves. Now if you look at the trumpet carefully, you'll see it's long thing, but there's 3 other bits of extra length of tube, and you notice with this particular picture that if we press the first button, we open the first valve and it lets an extra length of tube into the whole tube. Therefore we've got a longer tube and a lower note. Likewise with the second one and the third one. So therefore each of these 3 valves allow extra lengths to go into what is vibrating. So if you think of the trumpet and you look at these 3 valves, then think of the number of options we've got. We've got no valves, we've got 1 or 2 or 3, we've got 1 and 2, we've got 2 and 3, we've got 1 and 3, or we've got 1, 2, 3. And that's 8 variations, so we're going from 1 note up to the same note an octave higher.
Now, some instruments are reed instruments like the oboe, the bassoon, but far more importantly, the saxophone. And literally, you have a reed which is made to vibrate by you blowing over it. In the same way that you can make a piece of paper vibrate by blowing over it, maybe, like that, okay? Or, like you probably used to do in the old days when you were little, bit of grass in between there and blow through that. Bit of grass. You can do it again, make you feel young. Okay, now the reed instrument has a reed, and this is the reed. This is actually the reed here, which is held at this end so it's free to vibrate here. So if I blow it, mustn't put my tongue on there because it stops it vibrating. So that goes inside your mouth and you blow it like that. If we put it on the next bit of saxophone, got a slightly longer tube now. Put it on the rest and now many people think that the saxophone, you must be really clever to play the saxophone. Well, I'm not really clever, although I do like to play the saxophone sometimes. And the reason it's not really clever, it looks clever because it's got so many bits and so many buttons all over the place to press, but actually it's not far off a recorder. Look, once you've got it on you, you've got 1, 2, 3, 4, 5, 6, just like a recorder. See, easy. Then there's a little cheaty button on the back that you put your thumb on, there, and that puts everything up an octave. So that's how it works. Now, this one, that one does a flat, sharp. I use that one. And these are for the deep ones. There's 3 buttons here. I've got no idea what they do because I've never used them before. And I use one of these, but can't reach the others, so don't know what they do either. But you can get a good 2.5 octaves out of it by treating it like a recorder with a few extra buttons. Yee, good, isn't it? Oh, by the way, when I put it away, this is the stand. I put it in there. Once I was playing at a concert, and for the first half I was having great difficulty. I really couldn't understand what's going wrong. And at half time I looked and this was still in there. Doesn't work so well like that because the air can't vibrate so well. You can actually make your own little reed instrument, and it's a good thing to do with your grandchildren. Well, children if you like as well, they'd probably like it. First of all, you take a straw. Now this is a plastic one, and we don't like plastic very much, and plastic doesn't actually work as well as the good old what were they, paper and wax ones. So if you get paper straw, use that. Otherwise, this does work. Now, what you do is you take the straw and you cut a V shape into the end. Like that. Okay, so there's your reed. Now the only trouble is you want those to be reasonably close together, and that's the problem with plastic. It doesn't stick together very well. So I'm going to squash it as hard as I can for a while, and you don't have to squash it very much if it's a paper one, like that. Okay, and when I'm going to blow it, I want those bits to vibrate. So my lips go there. Don't put your lips on there, otherwise it won't vibrate. My lips go there with this inside my mouth, and hopefully it will vibrate. Grandchildren love that. But remember that the shorter the air column, the higher the pitch of the note. Don't do that at home, children. Right, well, you'll remember, hopefully, after all, it wasn't very long ago, was it, that the human ear can hear up to 20,000 hertz, 20,000 vibrations a second. So if we make sound that is at a higher frequency than that, the human ear doesn't hear it, and we call that ultrasound, beyond the sound range. And you all know that ultrasound is used in hospitals. It's also used in boats to detect where the ocean floor is, all sorts of things like that. And basically it's just an echogram. So you'll recall, you won't recall, but if you were near a cliff and went, ah, a little bit later you'd hear, ah, an echo. But basically it takes time for the sound to go there and back again. Now sound doesn't travel very fast. It's only 330 metres per second on average. That's the length of 3 football pitches in a second. So it's not that fast. So if you could time the distance between and then take the time for that, and you know the speed at which it's going, you know how far away the wall is. And the ultrasound works exactly the same as that. You send a little pulse of ultrasound down, and it reflects off whatever it is, the kidney or something, and back again. And the computer works out how long it took between sending out the pulse and getting one back. It knows the speed of sound. It's actually faster in a liquid because sound travels better through liquids and solids than it does through air. But anyway, it knows the speed and it works out how far down it is, so the computer can put together a picture. And that's how ultrasound works, whether it's a depth gauge on a ship or to look inside someone. The reason they use ultrasound is because it's a very high frequency and therefore a very short wavelength. And the shorter the wavelength means we can get lots of waves between the transmitter and the kidney. Okay, final thing then, I think we'll just mention this, and I've got a couple of diagrams to show you. The Doppler effect is all to do with waves and sound. Not to do with instruments, but it is to do with notes. Now, first of all, I'll start off with my famous impression of Lewis Hamilton. Okay, he's right up there. He's going to zoom past us and go down there at a constant speed. That's good, wasn't it? Okay. Well, what happened is when he was coming towards me, the pitch of the note sounded higher than when he went away from me, and that, although the pitch of the note that he was emitting was constant. And so when we perceive a moving transmitter of sound, if it's coming towards us, the frequency, the pitch is raised. If it's going away from us, it's lowered. Okay, and here's why.
Now this is how the Doppler effect works. When an object is moving along, it's still giving out sound waves at regular intervals, but it scrunches them up on the direction in which it's going, if you look at it, because it's sort of catching the waves up. So all those waves in front of it are squashed together. Now that's giving a shorter wavelength, which means a higher frequency or a higher pitch note. So if you were standing to the right of this picture, you would hear a higher pitch note. And if you were standing to the left of the picture, with all those waves coming towards you, much longer, further apart, then you'd hear a lower pitch note. And that's the Doppler effect. Well, ducks know all about this. Ducks, when they swim along, their little heads go backwards and forwards, so they make waves. And if you look at the picture, you can see the Doppler effect in action there, with shorter waves just in front of it and longer waves behind it. The police also use this system, and I'm going to tie this in with what we said about beats earlier. Now, a police radar gun sends out not sound waves, but radar waves. They're just like radio waves, but very short. And they hit the car and bounce back. But if the car is moving, it's just like it's giving out a higher frequency because it's coming towards the detector. And so therefore, what the device does is it compares the frequency which went out to the raised frequency which is coming back, and it puts them together and it gets beats, just like we saw before. And remember, the further apart the beats are, the bigger the difference in frequency. And so therefore it can work out how fast that car was going. Now, finally, you might be interested in what actually a sonic boom is when an aircraft is going very straight. So a sonic boom means that the aircraft is going faster than the speed of sound. So it's overtaken all the sound waves that it's being given out. And this represents a picture of where the sound waves might have got to. And the red line shows that the sound waves have all got to that point at the same time. So if you're the person on the ground there, what happens is when that reaches you, that sort of envelope of all the waves, you get the whole sound of the aircraft going across the sky gets to you all at once. And so it's just a bang. It's just all that noise put together in one moment. And that's what the sonic boom is.
Well, there we are. That's just about everything I wanted to cover. I hope you've enjoyed this little presentation. I hope you're a little bit wiser about sounds and music and so on than you were before. I hope you're still awake. Hang on. No, there's someone sitting on the sofa there who's asleep. Oi, wake up. Anyway, just to say thank you for watching, and I've got another subtitle. Hi, children.